Myself, Kedanam Patel from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, Electrical Engineering Department. Subject name is Electromagnetic Field, second year, fourth semester. Today we discuss about chapter number 1, review of vector analysis. Syllabus content, first one is vector triple product, second one is components of vector, third one is Cartesian coordinate system, fourth one is circular cylindrical coordinate system, fifth is spherical coordinate system, sixth is transformation from one coordinate to other coordinate system. Now, next, vector triple product. A vector triple product of three vectors A, B, C is defined as the cross product of vector A with the cross product of vector B and C, means A cross in bracket B cross C. Okay. Here A cross B cross C is a coplanar with the vector B and C and perpendicular to A. Hence we can write A cross in bracket B cross C as a linear combination of vector B and C. That is A cross in bracket B cross C is equal to X B plus Y C. Okay. In geometry and algebra, the triple product is a product of three-dimensional vector. Usually the name triple product is used for two different products, the scalar value scalar triple product and less than the vector value vector triple product. The vector triple product is defined as the cross product of one vector with the cross product of the other two. Here the vector triple product is defined as the cross product of one vector with the cross product of the other two. Other example like A cross in bracket B cross C is equal to A dot C dot B minus A dot B into C. This is known as triple product expansion, or we can say Lagrange formula, although the later name is also used for several other formula. Its right hand side can be remembered by using the mnemonic ACB to ABC, provided one keeps in mind which vectors are dotted together. A proof is provided like A cross in bracket B cross C is equal to B in bracket A dot C minus C in bracket A dot B, such that a more familiar mnemonic is obtained BAC to CAB as an back of the cap. Now, vector triple product formula here, A cross in bracket B cross C is equal to A dot C minus dot B minus A dot B into C, and A cross B in bracket over cross C is equal to A dot C B minus B dot C A. In general, the A cross in bracket B cross C is not equal to A cross B bracket over cross C. Here some properties of vector triple product is, first is vector triple product is a vector quantity. Second, unit vector coplanar with the A and B are perpendicular to C is plus or minus A cross B cross C divided by magnitude of in bracket A cross B cross C. And third one is A cross in bracket B cross C is not equal to in bracket A cross B cross C. And fourth one is in product A cross B, B cross C, C cross A is equal to A, B, C whole raised to square equal to A, B, B, C, C and C. The cross product is anti-commutative. The formula may also be written is different types, different ways. These formula are very useful in simplifying vector calculations. A related identifier regarding the gradients and useful in vector calculus is language formula. of vector cross product identity. Next, these are the different equations. This can be also used regarded as a special case of the more general Laplace or other different equations. The first is a cross in bracket b cross c is equal to b into a bracket a into c minus c in bracket a dot b. Note that the a cross in bracket b cross c is a vector quantity. It also have different types of general properties. First is a cross in bracket b cross c plus b cross in bracket c cross a plus c cross in bracket a cross b equal to 0. Second one is we have a general a cross b cross c is not equal to a cross b cross c. Third one is grade phase equal to del phi equal to I del by dx plus j del by del y plus k del by del z into phi. Fourth one is div capital F is equal to del into F is equal to del F1 by del x plus del F2 by del y plus del F3 by del z, where capital F is equal to F1i plus F2j plus F3k. Next is curl F is equal to del into F equal to I del by del x plus j del by del y plus k del by del z into where F is a F1i plus F2j plus F2j plus F3k, and curl F equal to in magnitude of ijk del by del x del by del y del by del z and F1 F2 and F3. If the geometric algebra is a use of cross product of vectors is expressed as the exterior product, a second cross product cannot be expressed as a exterior product. Otherwise, the scalar triple product would result. Instead of left contraction can be used. So, the formula of this vector triple product. It is a branch in a vector algebra where we deal with the cross product of three vectors. Okay. This value of the vector triple product can be found by the cross product of a vector with the cross product of the other two vectors. It gives a vector as a result. When they simplify the vector triple product, it given as an identity name of BAC to CAB identify. Now, since the cross product is anti-commutative, the formula may also be written up to primitions of the letters as a cross b cross c is equal to minus c cross a cross b is equal to minus c dot b into a plus c dot a into b. The other vector triple product definitions, like a vector triple product of the three vectors a, b, c is defined as the cross product of vector a with the cross product of vector b and c. Here the from language formula is followed that the vectors triple product satisfies like a cross b cross c plus b cross c cross a plus c cross a cross b. Here the a cross b cross c is a coplanar with the vectors b and c are perpendicular to the a. Hence we can write which is a Jacobi identified for the cross product. Another useful formula like a cross b cross c is equal to a cross b cross c minus b cross a cross c. Using geometric algebra, here it is also different types of properties, like first is a vector triple product is a vector quantity, unit vector coplanar with the a and b are perpendicular to the c. Here the equation is minus a is b to c equal to b Now here the components of vector. In the figure, the x-axis is the x directions ax, and in y-axis the ay is a y directions, and the perpendicular the in magnitude a, the this side is magnitude a sin I phi, this is magnitude of a cos phi. Okay, this is a parallelogram is a. So ax is equal to magnitude of a cos phi, and ay is equal to magnitude of a sin phi, where magnitude a is equal to magnitude of a bar. In 3-dimensional space, vector A has a 3 vector components. The component x is ax is equal to ax into I, where a tends to x is equal to axi, which is the part of the vector A along the x axis. The y component ay is equal to ay into j, and a tends to y is equal to ay into j, which is the part of the a along the y axis, and the z components so and so, which is the part of the vector along the z axis. A vector in a 3-dimensional space is a vector sum of its 3 vector components. These vectors are usually described in terms of their components in a coordinate systems. Even in everyday life, naturally invoke the concept of orthogonal projection in a rectangular coordinate system. For example, if you ask someone for direction to particular location, you will more likely to be told to go 40 km east and 30 km north, and then 50 km in the direction. So, in a rectangular Cartesian xy coordinate system, in a plane, a point in a plane is described by a pair of coordinates x axis and y axis. In a similar fashion, a vector, or we can say latex, in a plane is described by a pair of its vector coordinates. The x coordinate of vector latex is called the x component, and the y coordinate of vector latex is called y component. The vector component is a vector denoted by latex. In the Cartesian system, the x and y vector components of vector are the orthogonal projections of this vector onto the x and y axis respectively. In this way, following the parallelogram rule, the vector addition each vector on a Cartesian plane can be expressed as the vector sum of its vector component. Now, here also is another important example for vectors components. It is the customary to denote the positive direction on the x axis by the unit vector latex and the positive direction on the y axis by the unit vector latex head in latex. The unit vectors of the axis latex is defined at 2 orthogonal directions in the plane. In the shown in figure, the x axis and y axis and x and y components of the vector can now be written in the terms of the unit vector of the axis. Suppose you know the ball is rolling on the flat table at 15 degree from a direction parallel to the bottom edge, a speed of 7 meter per second. You may want to find out how long the ball will take to roll of the edge 1 meter to the right. Define your axis so the ball is at the origin initially and the x axis is parallel to the bottom edge of the table. Therefore, the problem breaks down to finding out how long the ball will take to roll 1 meter in the x direction. To find the time, you first need to know how fast the ball is moving in the x direction. The problem tells you that the ball is rolling at a speed at 7 meter per second at 15 degree to the horizontal, which is a vector. and 7 meter per second at 15 degree gives you both the magnitude and direction. What you have here is velocity, the vector version of speed. The ball speed is the magnitude of its velocity vector, and when you include a direction to that speed, you get the velocity vector small v. Now, to find out how fast the ball is traveling toward the table edge, you need not be ball's total speed but the x component of the ball's velocity. The x component is a scalar and you write it's like this v into x, and the y component of the ball's velocity vector is y v into y. Therefore, you can say that small v is equal to in bracket vx comma vy. That's how you express the breaking of vector up into its components. So these are the example of one type of vectors. Now, what is Cartesian coordinate system? First, the classification of coordinate systems. First is Cartesian coordinate system, second one is cylindrical coordinate system, and third one is spherical coordinate system. Now, what is coordinate system? The coordinate system is a basic idea which is used to define the position of an object in a given spaces. The position of an object is defined by coordinate of its concerned coordinate system. These coordinates are based on the measurement of position like a displacement, directions, projections, angle, etc. from a given locations. There are mainly three types of coordinate systems. Okay. Now, we are quite familiar with the Cartesian coordinate system for system exhibiting cylindrical or spherical symmetry. It is easy to use the cylindrical and spherical coordinate systems. The idea of Cartesian coordinate system was invented by the French philosopher, physician, psychologist and mathematician René Descartes in the 17th century. A Cartesian or rectangular coordinate system usually consists of three mutually intersecting perpendicular coordinate axes are set up which are labeled as x, capital X, Y and Z axis. The point where their axis x, y, z cross or intersect is called the origin 0, 0, 0. In rectangular coordinate system, a point P is identified by coordinates xi, yi and zi, 3 dimension, where these values are all measured from the origin. Okay. So, these are the figure of the location of point P in Cartesian. Okay. In this figure, in a 3-dimensional space, okay, at a point P can be directed or identified as the intersections of three surfaces. When the surfaces intersect perpendicularly, we have an orthogonal coordinate system. The point P xi, yi, zi is located at the intersections of three constant surfaces. Ranges of variables where x is equal to constant, y is equal to constant, z is equal to constant, and all three are planar surfaces. Here the Cartesian or rectangular coordinate system usually consists of three mutually intersecting perpendicular coordinate axes and set up which are labeled as x, y and z axis. Okay. Here is some other figure like a differential elements in Cartesian coordinate systems. Okay. All 3-dimensional x axis, y axis and p axis. This figure is constant surfaces and unit vectors in Cartesian coordinate systems. In this figure, mathematically there are the 3 differential elements corresponding to the length L, area A and volume V. These Three differential elements provide an integrating functions to differential coordinate system. The definitions of the proper differential elements of length means dl for line integrals and area ds for surface integrals. Okay. So, these are the characterized directly from the definitions of the differential volume or parallel piped like a dV per volume integral in a particular coordinate system respectively. In order to determine the differential element corresponding to the length, area and volume in Cartesian coordinate systems. Let us consider at a point P in the location x, y and z. If now each coordinate's value is increased by a differential amount by x plus dx, y plus dy and z plus dz. Okay. So, these are the first is differential length element. These are the distance between the 2 points P and P dash. Okay. See the figure and diagonal length. Second one is differential surface area element and third one is differential volume current element. Now, they consider the point P x, y, z is the rectangular coordinate system, that is the increase each coordinate by differential amount. A new point P dash will be obtained having coordinate. Thus, the dx is equal to differential length in x direction, dy is equal to differential length in y direction and dz is equal to differential length in z directions. Hence, differential vector length are also called elementary vector length, can be represented is dl is equal to dx into ax plus dy into ay plus dz into az. So, this is the vector joining or the original point P to new point P dash. Okay. See in the figure, now point P is the intersections of three planes, while point P dash is the intersection of three new planes which are slightly displaced from original three planes. These six planes together define a differential volume which is a rectangular parallel pipe as shown in this figure. Okay. Now, the distance of P dash from capital P is given by magnitude of the differential vector length. So, equation is dl is equal to under root dx square plus dy square plus dz square, and hence the differential volume of the rectangular parapet is given by the dV is equal to dx into dy into dz. Okay. Now, the defined differential surface area, the differential surface element ds is represented by ds is equal to ds into A. Now, thus the various differential surface elements in Cartesian coordinate system, the vector represent of these elements is given by different area. Now, these are the circular cylindrical coordinate systems. Okay. Figure shows the circular type coordinate systems. Okay. In cylindrical coordinate systems, at a point P is specified by the three coordinates, okay, rho, phi and z, where rho represents the radial distance, phi is an angular displacement and z is a axial displacement. So, see in the figure, in circular cylindrical coordinate system at a point P can also be identified as the intersection of three mutual perpendicular surfaces as follow. Here is a rho is a constant, a circular cylinder, then phi is a constant plane and z is a constant is another plane, and unit vector in a cylinder coordinate system are characterized as follow: a rho perpendicular rho is equal to constant. Okay. So, perpendicular to the circular cylindrical surface, then a phi perpendicular to phi is also constant and perpendicular to the planar surface, and az perpendicular to z is equal to also constant, which is also perpendicular to the planar surface. So, the cylindrical coordinate system is the 3-dimensional version of polar coordinate system. The surface used to define the cylindrical coordinate system are, first is like a plane of constant z which is parallel to xy plane, a cylinder, a radius r with z axis as the axis of the cylinder, and a half plane perpendicular to xy plane and at an angle phi with respect to xz plane. Now, the angle phi is called azimuthal angle. Okay. The range of the variable are the different angles, like r is a 0 less than equal to r less than equal to infinite. In phi 0 less than equal to phi less than equal to 2 phi, and minus infinity is equal to minus plus infinity. Okay. So, these are the different values of the cylindrical coordinate system. Okay, see in the figure, the point P in a cylindrical coordinate system has a 3 coordinates like r, phi and z, whose value lie in the respective ranges given by this figure. Okay. Now, the figure, the point P can be defined as the intersections of 3 surfaces in cylindrical coordinate systems. These 3 surfaces are is a constant which is circular cylinder with the z axis as its axis, where phi is equal to constant plane which is vertical plane perpendicular to xy plane making angle phi with the respect of xz, and z is a constant plane, is a plane parallel to xy plane. Okay. Next, the intersection of any 2 surfaces out of the above 3 surfaces is either a line or a circle intersection of 3 surfaces defined as a point P. Here the other important equations, first is like a differential length element is dl is equal to a rho into d rho plus a phi into r d phi plus az into dz, and second is differential surface area elements, third one is differential volume element. Okay. In cylindrical coordinate systems also main consider point capital P in bracket r, phi and z. In a cylindrical coordinate system, each coordinate is increased by the differential amount. The differential increment in r, phi and z are dr, d phi and dz respectively. Now, there are 2 cylinders of radius r and r plus dr. There are 2 radial planes at the angle z, angle is z and z plus dz, phi plus d phi. All these surfaces enclose a small volume are important. The differential length in r and z directions are dr and dz. In phi directions, d phi is the change in angle phi and is not the differential length. Due to this change d phi, there exists a differential r length in phi directions. This differential length due to d phi and phi direction is r d phi is the equations. Okay. Now, these are the spherical coordinate system. In this figure, we in a spherical coordinate system at a point P is specified by 3 coordinates. Here it is a r, small r is a constant, then theta and then phi. angle between x and this. So, where r represent the radius vector distance between origin to any point. Then the second coordinates is a theta. Theta is the angle between y axis and the radius vector r, and therefore theta is also known as the co-latitude or polar angle. And third one is the third coordinate of phi. Phi is an angular displacement between z axis and y is equal to 0 plane. Therefore, angle phi is also known as longitude or azimuthal angle. Okay. Now, this in spherical coordinate system, these surfaces which are used to define the spherical coordinate system on the 3 Cartesian axes. Like the first is sphere of radius r, origin at the center of the sphere. Second one is a right circular come with its apex at the origin and its axis as z axis. Its half angle is theta. It's rotate about z axis and theta varies from 0 to 180 degree. A half plane perpendicular to xy plane containing z axis, making an angle phi with the xz plane. So, thus the 3 coordinate at a point P in the spherical coordinate system are r, small r, theta and phi. So, these are the surfaces are shown in the figure. Now, here the r is a constant, all phi and theta is constant, and these are the first is r is a spherical surfaces, theta is a conical surfaces and phi is a plane. Okay. Now, this is the unit vector in spherical coordinate system are characterized as a follow. The importance is of the constant surface in spherical coordinate system. Here in previous figure, the point r, theta, phi can be represented in the spherical coordinate system is that the point P can be defined as the intersection of 3 surfaces in a spherical coordinate system. Now, here it is the transformations from one coordinate to the other coordinate system. Okay. If you given the cylindrical coordinates rho, phi and z of a point in the plane, the Cartesian coordinate x, y, z can be determined from the coordinate transformation and vice versa. In transformation from one coordinate to other coordinate system, here first we can see the transformation between cylindrical to Cartesian coordinate system. In other way, the different Cartesian or any versus coordinate systems is next slide. Okay. Here the Cartesian to cylindrical and cylindrical to Cartesian. In Cartesian to cylindrical, x is equal to rho cos phi and y is equal to rho sin phi and z equal to z, while cylindrical to Cartesian is rho equal to under root x square plus y square, phi is equal to tan inverse y by x and z is equal to z. Okay. The unit vector also are related by the coordinate transformations. Okay. Now, the rectangular to cylindrical unit vector transformations, okay, ax, ay, az to a rho, a phi and a z. The transformation of unit vectors from rectangular to cylindrical coordinate require the components of the rectangular coordinate vector capital A in the direction of the cylindrical coordinates unit vector using the dot product. The required dot product are a rho is equal to a Cartesian dot a rho is equal to ax capital Ax small ax plus ay plus az into a rho. Then after ax a rho, ay a rho plus az a rho. So, final equation is ax a rho plus ay a rho because of ax into a rho is equal to 0. So, then this way we can calculate the a phi and a z. Okay. So, these are the transformation from one coordinate to other coordinate systems examples. Okay. Thank you.